Hi everyone, my name is Linhao Meng from Vilanova University of Technology. I'm going to present our work, Class Constraint t-SNE, Combining Data Features and Class Probabilities. This is a collaborative work with Stef and Elzen, Nicola Pezzotti, and Vilanova. In machine learning classification tasks, we often look at two things together, data features and classification results. This helps developers understand model behavior and uncover potential problems. The classification results generally refer to the class labels assigned to the instances. Our focus is on class probabilities, which tell how likely each instance belongs to a particular class. The exploration of these two types of multidimensional data and their interplay is crucial in various domains. For instance, in document analysis, we often visualize and analyze topic modeling results alongside data features for comprehensive understanding. To visualize such multidimensional data, multidimensionality reduction is commonly used to condense patterns into 2D space. When it comes to data features, our interest lies in understanding the similarity between instances in terms of their feature values. General dimensionality reduction methods such as multidimensional scaling or t-SNE are frequently used to show such data feature structure. On the other hand, when dealing with the class probabilities, the focus shifts toward understanding the relationship between instances and classes, which we term class probability structure. An exemplary method for visualizing this structure is class radio visualization. This approach evenly distributes iconic representations of classes around a circle, which we will refer to as class landmarks moving forward. Instances with higher probabilities are positioned closer to their corresponding class landmark. Instead of using separate views for data features and class probabilities, imagine combining them into one projection view. Could this combined result help us extract valuable visual patterns more effectively? Let's imagine we already have clusters in the feature projection view. By adding class landmarks and further constraining the positions of data points and class landmarks, what kind of visual patterns can we expect? In the feature projection view, those well-clustered data points of the same class, say the green ones, tell us they are similar in feature values. Then, in the class radio visualization, we can see which instances have higher class probabilities, but we are not sure if they share similar feature values. Now, imagine we combine these two views. We are hoping the significant data feature structure manifested as main visual clusters is still there. Inside each cluster, we arrange data points in a way that those with higher probabilities are closer to their corresponding class landmark. Similarly, the two clusters with blue point of class B are put towards the class landmark, and inside each cluster, data points are arranged to ensure those with higher probabilities closer to the class landmark. In cases where instances are difficult to distinguish solely based on data feature structure, adding class information can enhance group separation. But beyond merely putting instances of the same class together, the most uncertain instances are dragged toward the edge where different class groups meet. Notice the yellow points. They look like the green ones in terms of features, but they are of class Y, so we expect these yellow points to move away from the main clusters in the combination view. Drawing inspiration from the projection methods for data features and class probabilities, and considering our assumptions of combined visual patterns, we introduce class-constrained t-SNE. This method combines data feature structure and class probability structure. Here, we gauge similarity in data features based on the proximity of data points. Additionally, class probabilities are conveyed through how data points are positioned in relation to their class landmarks. While we aim to maintain both data feature and class probability structure in our combination view, it can lead to some unavoidable interference. To address this, we introduce a user-adjustable parameter alpha, which allows for a balance between these two structures. This empowers users to focus on the weighted perspectives of interest. Furthermore, through animation, we can trace instances and facilitate comparisons among various projection results. So, what is our method? To preserve the data feature structure, we apply the original t-SNE to data feature values as our first cost function C1. For the class probability structure, we introduce class landmarks. Instances with higher probability should be closer to the corresponding class landmark. We borrow a similar idea from t-SNE, using probability distributions P and Q to model similarities between instances and classes in the original and 2D spaces. This gives us our second cost function, C2. Computed using Kullback-Leibler divergence, minimizing C2 is key to preserving the class probability structure. Then the question comes, how do we compute P and Q? Our goal is that instances with higher probability for a certain class to be closer to the corresponding class landmark, indicating a higher similarity between the instance and the class. Therefore, since we use P to model this similarity, we can derive it directly from the class probability. Specifically, for instance I, the probability distribution Pi is simply the given class probability of instance I. Let's look at how we compute probability distribution Q, which measures similarity between data points and class landmarks in the 2D space. Similar to t-SNE, we determine distances between the point I and all class landmarks. Then, using the student t distribution, we convert these distances into probability denoted as Qi. Following the above approach, we compute P and Q for all instances, and then sum all Kullback-Leibler divergences as the cost function C2. However, this approach may not always yield a stable result. For instance, consider an instance with an equal probability of 0.5 for classes B and R. Any 2D placement of this instance ending up on the perpendicular dissector of class landmarks would satisfy this probability constraint. To address this, we introduce a distance penalty D to ensure there is only one optimal value for each data point. In the example, this would be the midpoint of two class landmarks. As placement of data points impacts both data feature structure and class probability structure, we define the cost function for data points as a weighted sum of C1 and C2. By adjusting the alpha value, we can generate a projection view with a merged perspectives of interest or even animate the projection. Throughout the optimization process, each data point can be viewed as receiving a weighted force from all other data points and class landmarks. While the placement of class landmarks only affects class probability structure, we define cost function for class landmarks as C2. Throughout the optimization process, its Each class landmark can be understood as receiving false from all the data points. In our implementation, the minimization of cost functions is achieved by gradient descent, which you can find more details in our paper. To validate our method, we first generate a 10-dimensional synthetic dataset, which comprises 5 Gaussian clusters labeled as 4 classes. Next, we trained a random forest model with 70% of the data and applied it to generate class probabilities for the entire dataset. We then applied class-constrained t-SNE using 5 alpha values ranging from 0 to 1 to obtain continuous projection results. As you can see, by combining data feature structure and class probability structure, some visual patterns emerge as expected. The 2 clusters of the same class 3 shown in the class feature structure are still preserved but get closer when alpha equals 0.5. For the ambiguous cluster with classes 0 and 1, data points of different classes slightly get separated but are still within one cluster. We can also see some outliers, which are unrepresentative of both perspectives, or whose data feature similarities and class memberships conflict, are pushed out from the main cluster. We also apply our method to 2 real-world datasets. One is the Fashion Minutes dataset, the other is the VIS publication dataset, which shows its functionality for classifier analysis and document topic analysis. Let's consider a simple example to see how our projection results aid in classifier analysis. When alpha equals 0.5, the circled blue points are not located in the Chaucer cluster of blue points. When alpha is set to 0, these points scatter across the projection view, suggesting they are not aligned with the main Chaucer features. However, when alpha equals 1, they show high probabilities for class Chaucer. Upon verifying the original images, we confirm correct classification. In another case, a circled green point is classified as stress, but it truly belongs to Chaucer based on its data features. This highlights the value of examining instances where data features and model results differ. However, identifying these data points from the projection of a single perspective can be challenging. We've also conducted a qualitative and quantitative comparative analysis with a baseline method. For a deeper dive into the details, please refer to our paper. To conclude, we introduce class-constrained t-SNE, a dimensionality reduction-based visualization method, which integrates both data feature and class probability structure into one single projection view. Users can control the balance between these 2 structures with an interactive parameter. As future work, our approach for incorporating class probability information has the potential for adaptation to other dimensionality reduction techniques that employ explicit loss function and require iterative optimization of data points, such as UMAP. Our method can potentially be accelerated by integrating it with accelerated variants of t-SNE.